Hello, can everyone hear me? All right, I am told it's time to rock and roll, so let's get started. I'll do the pre-panel announcements first. A reminder, while you are inside the track room and the panel is going on, your mask must fully cover your nose and your mouth. Exhibit. Look at these fine exhibits of proper masking up here. We're asking that people not eat or drink for long periods of time in the track room because of this. Sorry, if you want to eat your dinner, you can step out for a second, come back, or you can put your mask on in between drinks of water or bites of food, whatever. I have stopped the panel today because not everyone in the room was masked, and we waited for them to put their mask back on before we continued the panel. Please don't make me do that, and wear your masks for the whole panel. Thank you. Other announcements. Let's see, what else have we got? Please make sure that you silence your cell phones. I love music as much as the next person, but this panel does not have a soundtrack. We are collecting for the DragonCon charity. Someone wave the DragonCon charity bin. It's a bucket. It's called Open Hands. Please put money in to the DragonCon charity bin. We will be clearing this track room. Loving the generosity of the panel. We will be clearing this track room at the ends to make room for our next event, so make sure that you follow the instructions. I think we've been clearing that way, but someone will tell you which way to clear the room after the panel. And I think that's it. So welcome to, I have forgotten the precise name of this panel. Fantastical and Real Energy Production. I wasn't sure if it was fantastic or fantastical. I'm Jennifer Greco. I'm an astronomer turned science teacher. I'll be moderating this, and I'm going to let my panelists introduce themselves.
Hi, my name is Jeff Hubbs. I'm a contract consultant working in the fields of energy systems and climate change research.
My name's Ryan Consul. I teach engineering up in Canada.
I'm Tori Stenmark. I'm an organic chemist at Shoreline Community College near Seattle.
Hi, I'm Adam Friedman, and I'm an environmental scientist who studies air pollution.
So the purpose of this panel is to talk about sort of some real methods of producing energy, what the landscape is going to look like in the future, and then some fantastical ones. So let's start with talking about what the landscape looks like today. So can you all comment on some current methods of energy production? Do you have a favorite?
Ooh, favorite? Hydro. Hydro's great. Hydro would solve all of our problems if there were 1,000 times as many waterfalls or 1,000% fewer people.
Or if water was really, really, really dense.
Or if water was vastly heavier, but that would cause all sorts of different problems.
That might cause different problems.
Biochemistry would like a word.
Kilometer-high lakes of mercury, and now we're talking.
Yeah, but hydropower is incredibly great because it's basically solar power, but with much less complicated work. And water just constantly flows downhill. And as long as you've got a big hill, then you've got electricity that you can turn up, you can turn down, you can adjust the amount of water flowing through your system, which solves all sorts of big grid problems. The biggest problem is that you need many more Niagara Falls around to make it sort of scalable to population.
We do a surprising amount of hydro in Washington State. Works great, but yeah, geology says you got to have more waterfalls.
Primary energy sources on around the entire Earth. To a first approximation, it's mostly fossil fuels. Gas and coal. Below that comes nuclear. Below that comes all the renewables, to include hydro, sadly, until we get the kilometer-high lakes of mercury. And part of the goal of the post-fossil energy systems transition is to try to raise the proportion that's done with renewables at the expense of that which is produced by fossil fuels.
I'm a little bit concerned about how casually you just keep throwing out the phrase kilometer-high lakes of mercury.
They're very useful.
Does no one else feel like this might cause problems for, life?
Some of us have seen some of the brain scans. You don't trust me. Although, to be fair, liquid mercury is not nearly as bad as organometallic mercury. That's the real fun stuff. You familiar with the phrase "mad as a hatter"?
Yeah.
Yeah, organomercury.
But I mean, the kilometer-high lake of mercury is something we'd make. You get all the mercury that you can find. You put it in a big water tower, basically, and then you use a renewable source to pump it up the tower, and that's your battery. Because one of the big problems we have right now, especially with renewables, is energy storage.
Right.
Even if you can get enough wind or solar, that only works when the wind's blowing and the sun is out. And batteries are kind of a problem, but if you've got something that will store all of your energy in, say, a giant kilometer-high lake of mercury, when the wind's blowing, you pump it up to the top, and when the wind dies, you let it flow down.
The amount of energy that's stored in lifting anything is proportional to the product of the mass and the height.
Don't tell me, tell the microphone.
Yeah, eat the mic.
And the density of mercury is like 11.
They can't hear you. You need to eat the mic.
It's like 11 grams per centimeter, whereas for water it's 1. And for rock and concrete it's 2.5.
Lead is denser, right? Or
Yeah, but you got to keep
like
it
13
hot.
Yeah.
That's why
okay.
mercury is great.
Mercury is great.
I mean, it's not like molten lead is better than mercury.
Engineers, man.
No, it's not. I think lead is like 8.
Yeah, no, it's not.
No, mercury's 13. That's what it is. Mercury's 13 grams per mil.
Oh, okay.
I knew 11 wasn't feeling right. Do I need to know
Yes,
that number?
The problem
for
wasn't
this?
the toxicity; it was the density.
Yeah. Well, when you think about it, apparently there's things about toxicity we haven't cared about for the past century.
Oh yeah,
So
yeah. Burning coal has killed more people than any other nonsense we come up with today. How are you feeling? What's your favorite source of energy?
I mean, I'm generally fond of things like ethanol and methanol because, like, they actually can be set on fire. So, yeah. Although biodiesel is great. We've got a biodiesel truck on campus, and they get their bio to turn into, because what you do is you get, grease of some sort, and what you do is you go down to your local fast food restaurant and you say, hey, the next time you change the fryer, can you just give me your used oil? And they crack it into biodiesel. But it still smells like McDonald's French fries. So you go over and you're admiring the solar energy, renewable energy stuff on campus, and they're very, very proud of this. And you're like, wow, I could just kill for some French fry. Oh, that's why. Because the exhaust smells like French fries.
Yeah. So this is, well, okay. So to start, I should clarify, a lot of my sustainability
Get closer to
background
the
is
mic.
more in recycling. So something that I've seen that isn't a primary fuel source, but which you can do, and you take styrofoam and you essentially dissolve it in fuel, and that increases its efficiency. It also can be used to make napalm. So
I was gonna say that exact phrase.
Yep.
I'm having anarchist cookbook flashbacks for anybody of a certain age. Oh no, we're very serious.
You have to laugh, otherwise it's bleak.
Yeah. This is laugh or cry.
Everything we do at Sidetrack is 100% serious.
and yeah,
Do we still have any of those?
Teeth.
I was going to ask if we still had the Rainbow Chaos Goose badge ribbons or if those went home with...
Yeah.
Excellent. If you wish to be a Chaos Goose, you are in the correct place. And after the panel, you should get a badge ribbon saying so.
I mean,
Yeah,
I
what
don't
else
know.
have we got? So what have we had not covered? Nuclear. Nuclear's pretty good. It's got a couple issues. The ones that we think are nuclear power issues. Sorry, I should really get into this. Hi, Mike. How you doing this evening? So the nuclear power issues we think are issues with nuclear power, you really aren't the big ones. It's investment in getting the new plant up and running, decommissioning them when they're done, and when a nuclear plant is running, they're very, very level, which is a problem because our use isn't very, very level. So when we all turn on our air conditioners, we want more power. When it gets, temperate and middle of the day, we turn down our power. Industry needs power at different levels at different times, and nuclear doesn't want that. It wants level. So on top of nuclear, we would always need something that can deal with the ramping. And the nuclear can basically just give our lower threshold for the least energy we ever need.
Now there is a cradle to grave life cycle about fission products for nuclear reactors. I mean, from mine to disposal of spent fuel, and ultimately, well, for instance, if out west, if you kind of know where to look, it helps. But if you look on Google Maps with satellite turned on, there'll be places out in the desert where there's this gray rectangle, just a nice, very clean gray rectangle. If you zoom in, it looks like the edges of that rectangle are kind of beveled. But those are places where the Department of Energy has contracted to bury the places where uranium was mined and the equipment was used to begin the separation process into something that you can use in a reactor. If you go up to those sites, they're just long fields of rock, just rocks piled up. And that's to keep the dust down and try to control the spread of contaminated materials. We still, it's not just national but worldwide, we have not really addressed the issue of what to do with spent fuel. For the most part, it is kept at the reactors where they're expended, and with apparently in perpetuity. One of the things that went wrong at the Fukushima Daiichi plant in Japan after they had that tsunami a few years ago was the spent fuel pool lost cooling. They keep that stuff immersed in water to keep it cool. I mean, it's still it's no good for using in a power reactor anymore, but it's still quite radioactive and still emits a lot of heat as it decays. We don't have a repository for keeping that stuff yet, even after decades and decades of trying.
And most of that isn't because we don't know how, it's because nobody is willing to have it in their area.
Well,
And like, there's places in America, in North America, that are like, this is where we're going to put it. And they figured that out 50 years ago. And then people in that state are like, nope, not in my backyard. I'm like, it's 1,000 miles from you. It's still in my state. And that fight has been ongoing, and which is why all of our nuclear fuel is still on site, which is kind of the worst place to put it.
About 30 odd years ago, Sandia National Labs, which is part of the Department of Energy, released a study trying to design giant facilities for nuclear waste disposal with a marking system sufficient to communicate to people 10,000 years from now, do not disturb this place. Nothing of value is here. In fact, one of the teams that was part of that report was one that Carl Sagan served on. But they had elaborate systems of berms and symbols and things that were just psychologically meant to be foreboding, just to keep people away from it.
so they call that nuclear semiotics. And the first one of them reads, "This is not a place of honor."
Right.
So you're never going to find that in the Fire Nation, I'll tell you that much. It's great stuff, though. Like, it's really unsettling and interesting if you look into it. The danger is here in your time as it was in ours.
Yeah,
Nothing of
it's-
value
it's-
is hidden here.
It's very poetic, the way
yeah,
it reads.
Yeah.
I want to look this up now. I knew nothing about this. I'm learning stuff. I mean, I don't know if I'm allowed to comment on my own question, but I'll do it anyway. Having just returned from Europe, I think my favorite one that I've learned about in the last 2 years is I was in Sweden, and what they can't recycle, they incinerate. They generate energy by incinerating their non-recyclable trash, which I thought was literally the coolest thing ever. So that's my new favorite method of energy generation is trash burning. Solves two problems at once because they don't put anything into landfills over there either.
It does that one runs into a very weird problem, is that when you get better at packaging your products, your energy supply gets worse. They're like, all of our products are fully recyclable. And they're like, we can't turn the lights on anymore.
And yet it takes less energy to create less packaging.
It's true.
I don't know if that's win-win in the end, but
I mean,
But
I
it's
don't think that
complicated.
turns your lights on, though.
I mean,
Like,
the
your lights
moral
are
of-
still off. Now you're making your less packaging in the dark.
that way you don't have to use clear packaging.
Now we're back to the Tower of Mercury. Any other comments on what?
We'll probably get to pumped hydro somewhere on this panel.
Not high enough, not dense enough. That's my story.
We are going to open for questions at the end from the audience. In the interest of respecting the fact that everyone who asks a question has to ask it into a mic, I'm not going to open for questions until the end. But hold on to them and we will get to them. Well, if no one has any more comments on current energy, I guess let's jump to the future of energy. So are there any weird, wacky, awesome future energy ideas that you are excited about, that you think are too crazy to work, that you think are somewhere in the middle?
Let's go somewhere in the middle. Do we
right.
want to talk about fusion?
Always.
So,
Big one.
fission, nuclear energy as we have right now is fission. We take a very heavy atom, we split it in half, and it releases some extra energy which we use to boil water, which runs our turbines. Literally all of our, almost all of our energy is just boiling a kettle to make a thing spin. And that is what our nuclear reactors do. Fusion is the opposite, is what our sun does. We take a couple hydrogens, smack them together, they make a helium and a little bit of extra energy. You do that a lot, you get a lot of extra energy and a sun or a hydrogen bomb. And it is a perfect energy source if we can make it work.
What about cold fusion, Ryan?
Well, that's a thing that we will start looking into when we can get hot fusion to work. Yeah.
Val Kilmer did it.
Wrong track. Cold fusion is a science fiction wet dream. It's, fusion, but not so hot, not quite so hot. One of the problems with fusion is it's very hot.
Like star.
But there's been lots of very cool news about fusion, about cool new magnets that'll get our tokamak reactors to work better, and like some fusion experiments that have actually netted positive energy, because one of the problems with fusion is it takes a lot of energy to get going. And so they've been able to start fusion reactions, but not keep them going long enough or hot enough to net positive reactions. The joke about fusion, and it's been a joke for all of our lifetimes, is that fusion is 20 years away. And it has been for about 60 years.
Yeah.
It's still 20 years away. Even if tomorrow you woke up and somebody went, we've done it, we've cracked fusion, we can start making fusion power plants tomorrow, the plants, the infrastructure would take 20 years to get in place. The price of copper and helium for the magnets and the cooling would skyrocket. And the concrete we would need to pour to make these would probably take almost another decade of those plants running to offset the carbon footprint of the concrete. So it sounds real good, and it might be someday. But it's got problems. Anybody else have fusion rants? That was my fusion rant. And, any other cool near future, maybe, power supplies?
I don't know a whole lot about it, but I'm intrigued by tidal power.
Ooh. Yes. Do you know much about tidal power? I feel like I don't want to talk all the time.
Well, here's same thing as pumped hydro. Not very dense, not very hot. If you're looking at a few feet of tide with something that's only 1 gram per cubic centimeter, you can only get so much energy out of that, no matter how fast you can take it. It might be useful when there's no more practical alternative in remote location, but considering that it's something you can't navigate ships through, it's kind of just a low power, low energy solution. Compared to the sorts of demands that civilization places on the energy system, it's got nothing.
Is one of you able to explain how tidal power is supposed to work for those who don't know what it is?
Well, there's more than one way you can do it. The simplest way would be something where, let's say you take a piece of shoreline and you wall it off, except for one place, one little point in it. And when the tide comes in, you open that one little place, and your enclosed little water pen there fills up with water. As the tide starts to go out, you close that gate and run the discharge through pumps. not pumps, impellers to run a generator. Again, how much tidal change do you get? A few feet. So the amount of energy you can derive from that is limited to how much water you can capture in your enclosure. Well, how many square miles are you going to devote to that? And can you get enough power going through the number of sluice gates or generators, whatever you would need, to be able to handle the thing filling and draining twice a day?
And this is this brings up one of the problems with a lot of our renewable sources. When you look at the raw numbers, the energy available in the tides is massive, more than we could ever use.
Yeah.
The amount of energy available in solar, more than we could ever imagine using. The amount of energy from the wind, more than we could ever imagine using. But actually capturing it requires so much infrastructure that we destroy the entire landscape doing it, alter the ecology of the planet, attempting to capture the tides, attempting to capture that much sun, attempting to capture that much wind.
Mm-hmm.
So locally, in the best places, all of these are really good solutions. You got a lot of sun and a lot of good places to put solar panels. Yeah, put solar panels there. You've got really high tides and you don't have like a coral reef. You could do some cool stuff with tidal energy. You've got high winds and stable high winds. You put wind there. But none of these work everywhere. They really only work in the places that they work for. They're welcome to Tautology Club. Which means whatever we're going to do is going to be a puzzle piece solution of trying to figure out what is best for this place. And it's even in those places will likely be a mix of things going forward as we start to run out of crushed dinosaur to burn.
Yeah. Good time to talk a little bit about solar. The way I like to characterize solar to people is you're talking about having a magic device with no moving parts. All you have to do is shine light on it, and on two terminals in the back, you get some voltage at some current, which means some power. That's unbelievably cool. It gives you a way to open an aperture to capture free energy from the sun. There's no one to pay, no one to buy it from. It's just there. However, opening that aperture costs money, and it takes space, obviously. Otherwise, it would be an aperture. So the challenge of this is being able to make enough of these magic devices to do this, being able to site them, protect them. In fact, one of the biggest means of loss in solar farms, some part of the country, gunshot. They a lot of just fail from being hit by bullets more than any other failure mode.
Not from being shot at mostly, but by hunters and people target shooting
Both
in their backyard,
Like,
and just people who think it's fun to shoot at solar panels.
or just happy fire. Just
Oh,
happens to hit.
America!
So it's
We're sorry.
And the other issue, of course, is adapting the seasonal changes and daily changes to sunlight to the kind of demand we have. We kind of made ourselves an always-on society, and we aren't accustomed to something where we have a power source that it really just doesn't give you anything for a certain number of hours a day.
Yeah, after living in Sweden, where in December it's dark 20 hours a day, I have some questions about the seasonalness of solar in certain parts of the world. In the summer there, it would work very well because the sun never goes down, but in the winter it might be a problem.
And still, you'd have to rotate it around, to catch the sun as it went.
Yeah,
Which I think brings us back to the storage problem we were talking about earlier anyway.
It's not the whole problem,
Reminder
but yes,
to
storage.
Have your masks covering your nose and mouth at all times, please.
Yeah, storage is an interesting problem. There's a couple clever solutions to storage. So storage, we put, your battery. You've got energy generation, thing that makes the power, and then if you make too much, we want to keep it somewhere so we can use it later. Batteries are the one we're familiar with. One of the ones that people are playing with, and we've complained about the problem with the density of water, is if you have a reservoir and you have surplus energy, you can pump water up into the reservoir, and then later it can flow back down. There's limits on that due to volume. A very cool combo that I've seen is called photovoltaics. It's a wonderful portmanteau if you're an energy geek. Photovoltaics are solar panels, but what they're doing is taking solar panels and floating them on top of reservoirs. And so it is both a hydro plant and a solar plant, which solves one of the big problems of solar panels, is figuring out where to put them. Because it's not just putting them in a good place, it's then connecting them to the network. But if you've already got them attached to a hydro plant, everything's happy. If you have something like a reservoir, it doesn't even need to be a hydro plant. When you've got too much sun, you pump things into it. When the sun goes down, you let it drain out. Your photovoltaics just stay floating on the surface, nice and flat. Couple things, I saw a wonderful paper on this, and they were talking about the best places to put it, and they thought only about the size of the reservoirs and the gradient of the hills, and they talked about Canada and Russia, forgetting entirely about winter. So it's not a perfect solution, but it's very cool.
Any other thoughts on the future of energy production?
The real future energy.
I was going to say, the real future before we get to the not real future.
Ooh, there's one more cool battery I just remembered.
Go for it.
It's a sand battery. It is made entirely out of sand.
What?
Yeah, it's in one of the Norwegian countries, up Scandinavia, not Norwegian, but up in Scandinavia, somewhere in there. And when they have surplus energy, they just run it through a big resistor and it's just a big heater into a massive, well-insulated silo of sand. And then, when winter comes and it's cold and dark, they siphon that heat off to heat the community.
Now,
What?
It's deeply inefficient use of their extra energy, but it doesn't matter because it's surplus.
it is power limited because heat does not transfer very quickly through sand. That's one downside to it. Is there any chance at all that any of you were here a few years ago when I described my modeling of the Stone Mountain flywheel? You were there for that. Oh, I'm sorry. The Hubs Memorial flywheel at Stone Mountain. If I can't name it after myself, why even think it up? It was a thought experiment that I did, trying to figure out what it would take to manage the storage that would be required for a 100% solar photovoltaic energy source for the state of Georgia, given business as usual demand. The flywheel was roughly barbell top shaped, 500 million tons, a kilometer long, 26 RPM in July, 2,000 miles an hour at the tangent. I don't know if this is even mechanically possible, but my point was just to show what it would actually take. And yeah, I did the same modeling with batteries, and yeah, it'd form a cube 400 meters on a side. So, I mean, again, that's an extreme case, 100% solar. But the closer that the more you have intermittent energy sources for electrical production, the more proportion of that you have, the more you have to rely on storage to adapt that supply to our demand, unless we're going to change the demand either by reducing it or changing its periodicity.
This is one of the weird things. Us heavily industrialized countries are much less able to adapt to that changing landscape. So there are many countries around the world that have intermittent power. They're fine with it. They just deal with it. They're like, oh, I've only got full power for 3 hours a day, 6 hours a day. Fine. That's how we live. We cannot cope with that. If our power went off right now, a bunch of us would just die. We get too hot. The accidents outside from all the streetlights turning off would be incredibly fatal. None of our airplanes could land, but these countries are well adapted to it because it's just how it's always been. So they can take tidal, wind, solar, slap it on their house, slap it on their bicycle. They're fine with it. It's great. It's an upgrade. Us, we're very addicted to burning dinosaurs.
Yeah.
think this is as good a place as any to transition into the science fiction section of this panel, which is, I mean, we've all probably watched some science fiction. Do you have some favorite?
No.
If you haven't, then make something up in the next 5 seconds. No, do you have a, favorite, for lack of a better word, method of energy generation that often shows up in fantasy or sci-fi?
Come on,
This is
Star
for
Trek
the
fans.
panelists right now. Nope, panelists first.
Okay.
So I'm asking the panelists for their favorite fantasy method of energy generation, especially if there's one that you wish was real or think might be real someday.
I think that those of you that can't generate your own fire are just going to be out of luck.
So yes, so choreographed dance
Absolutely.
is
Yeah.
effectively.
Those of you unfamiliar with the source material, it is Avatar: The Last Airbender, where people are able to do martial arts to manipulate the classical Chinese elements of earth, air, water, and fire. So the firebenders are great at generating our own fire for whatever purposes we might need it for. And, then you've got wind power, right, with the airbenders, and you've got hydropower with the waterbenders. And the earthbenders can probably deal with this liquid mercury. And, if they're magically containing it, I'm less cranky about it.
Actually, now I feel like that's a worthy question. If we had to pick one as our energy production nation, or they were competing on just producing electricity,
Those be the guys.
which would you pick? Which of those elements would be best for making energy?
You already
making
know what my
electricity?
answer is.
I feel there's a bias on the panel.
I would argue air, if only because they need the least. They probably would use the least energy out of any of the other four.
Okay.
That's fair.
Or the three, sorry.
That's a
We're not
good point.
we're not forgetting, we're ignoring.
Headcanon.
If your sister is bending lightning at you, then you've got generating electricity right there. So that's a good option too.
So,
But it's inconvenient for the narrative we're constructing right now.
so what do they do on Star Trek, guys? Come on. How do you run the Enterprise? Thank you.
Antimatter.
Matter-antimatter reaction. Now, antimatter is a real thing. We don't have any around here. If there is, you'd know it in a hurry.
You would not have it for long.
Yeah. Through some quirk of cosmological evolution I'm not prepared to explain, the universe developed with very, very little antimatter in it, almost none. But if you had I went through this in my panel from last year. If you had a nickel coin made of antimatter, and it would look just like a real one, there's nothing strange about antimatter, and a real nickel coin made of matter, and combined them, the energy that would be released would be about like a tactical nuclear weapon. And so what Roddenberry kind of hashed out in his head was that you control that reaction in some way, and you can run spaceships faster than light, or scorch entire planetary surfaces.
I mean, it's true. The challenge is that's probably more of a storage mechanism again, because if you can get the antimatter, if we could just find a bucket of it somewhere, it would be great. Great's a complicated word. But if we can generate it, then we could store a lot of energy in antimatter, and then when we recombine it, get the energy back out quickly. Terrifyingly quickly.
Terrifyingly, yeah.
For those in the audience who are not familiar with the physics that we're discussing, the problem is that when you put matter and antimatter together, it blows up. So the storage problem is that you have to store antimatter, so it's not touching matter, but the only storage devices we possess are made of matter, and I feel like you can all see where this problem is going at this point.
Yeah, some kind of
Mildly inconvenient.
some kind of
Mildly
containment.
inconvenient, yeah.
Something magnets, right? Isn't that the solution?
Yeah.
Magnetic levitation?
The answer in physics is always something magnets.
Yeah.
That is correct.
It's really important to have a handy mental Rolodex, if you will, of what are the quick excuses that buy you just enough time to come up with the real answer. In chemistry, it's a combination of steric and electronic effects.
Assume a vacuum.
Yeah, right?
Assume a
See?
vacuum.
So, something magnets is your physics time killer.
Right. Panelists, any other favorite fantasy, sci-fi, etc.
Oh, there's the Matrix.
Oh.
So I have a better explanation
Copper
for the
top.
Matrix
Do you?
versus humans as batteries, which is not my idea, but I really liked it. This author, you've probably never heard of him. His name is Neil Gaiman. That's it.
Oh, yeah.
Actually wrote a short story that posited, like, paid licensed Matrix short story that says that they're actually using the human brains as their computer simulators. And I like that one much better because you don't get any useful fuel. The amount of energy it takes to keep a human alive in a pod doing nothing is much more than you're going to get back out of them. Like, it's just not efficient.
Well, if we're talking authors, anyone who reads Brandon Sanderson, I mean, the central conceit is all those different, worlds, whatever, they have their own magic systems. But one of them, Stormlight Archive, for those of you that are familiar with it, it is literally light from storms. And it's used to power the magic system. Someone else could explain it much better than I could. But it functionally works like an energy system in a lot of ways. But going back to what we're talking about, you can't take it off-world. There's a whole subplot in the most recent book of where there is a group of people who is trying to take it off-world and go elsewhere with it, and they can't because they can't store it. And so you come back to this, different planets, different regions are going to have different energy sources that are going to work better for them, like we do here. So it probably wasn't purposeful, but I think it ended up kind of making a weird parallel of the fact that some places are going to do energy better, and some places are going to do worse.
Strong metaphor, bad physics.
Yes.
I mean, in my current capacity as a wizard, I feel obligated to point out that magic is the answer to everything. Okay, do I have a mic runner somewhere who can facilitate some Q&A? So stick your hand up. To the audience members, when you're asking a question, please make sure that you eat the mic or we will also not be able to hear you. You really have to commit to the mic eating because of the masks.
You've seen us fail for 40 minutes now.
Yeah, you've been watching
Learn
us fail
from
for
us
40 minutes.
and
Learn.
succeed.
So the way we're doing questions, it's like by section, and then we'll come back around, so everyone's aware.
Yeah, it's so she gets as much exercise as possible.
Hello? Yes, thank you. Is the real future of energy distributed or centralized production?
Yes.
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 That was easy.
Go ahead.
What's the split?
So, it is, I think, as we were saying, that regions are going to have the, a bit, some things are better for different regions. And that includes the amount of centralized and distributed. If you have a really distributed population, a distributed power source might be a better idea. Especially if you've got you guys are coastal and there's only 200 of you. Yeah, we can use tidal power. If you're New York City, that's not going to work. If you've got hundreds of millions of people in a really small area, you're going to need a centralized system to navigate all of the different inputs. Because we already use many different inputs into these systems. And when you have lots of population, lots of industry, lots of demands, it's better to socialize. I know that's a dirty word down here, but socialized energy, as in we have many inputs working together for the benefit of all of the people who are attempting to use it, and a central system distributing it carefully and making sure it all gets managed. Distributed populations, that's much less important.
Okay, that's a pro. I'm going to give you a con. Okay, technologically speaking, in just very step back and look at terms. Generally speaking, it's not as good to have many little things than it is few big things. We did not do a thing, for instance, where didn't we have gas piping to residences and businesses before we had electricity? Okay. Well, things didn't develop such that we've got gas engines, natural gas-powered engines in our house to run generators. Instead, we have a separate electrical distribution system so we can centralize and consolidate generation facilities and have them be more powerful, and then we have mechanisms to be able to distribute that over a large number of people, than to have a lot of little things.
I think because we like to complicate things even more, different systems are most efficient at different levels. Nuclear plants are only efficient at huge. Backyard nuclear plant, bad idea for a variety of reasons. One of them is efficiency. You burn through your fuel much less efficiently at a small level. However, things like a generator that'll power your phone in a stream is a terrible system at scale. So yeah, it depends a lot on the situation, but for like power at large, absolutely. We need big things.
In the interest of time, let's move on to the next question.
But I have so many words.
I know, I'm sorry.
It's okay.
I read about somebody has developed, it's hard to describe, but you can drill way deep, deep, deep down to where the earth is hot, and they can like fuse the sides so it doesn't all cave in.
Yep.
And you can basically build your own geyser. For
Yes. Geothermal energy. Few varieties of that. You want?
Nope.
Iceland.
Yeah.
Iceland.
Iceland. Yeah, if you have a bunch of geological activity, volcanic activity, that's pretty easy and you can do a lot of cool things. Iceland's doing a bunch. Japan does a bunch. If you are in a very tectonically stable area, you can't get as much energy out, but you can use the ground as a battery for thermal energy. You can get heat systems where you use a heat pump to pump all of your extra heat into the ground during the summer, and then pump it back out to heat your house in the winter. But that only works in places with really sort of even seasons. If it's always hot, that's useless. You just boil your ground.
Yeah, it's power. It's got natural limits to how much power you can.
Yeah.
You can do that way. Again, you don't want to boil the water underground, nor do you want to freeze it. And I don't know what happens when you and your neighbor and your neighbor and his neighbor and their neighbor are all doing it at once. I don't know. I'm not sure to what extent that starts cooling down or heating up everything to everyone's disadvantage.
So I was wondering if any of the panelists could talk about the news out of MIT recently about a battery made out of aluminum, sulfur, and salt as a storage capacity for the various other methods of producing energy as a storage mechanism.
I read the paper. Or a couple papers on, like, there's a lot of cool stuff coming out of battery technologies, and there's problems with lithium ion, which is sort of what a lot of our rechargeables are right now. And there's optimism around sulfur-based batteries, but they have a lot of problems. MIT's come up with a couple of solutions, but it's not nearly approaching market. And I cannot speak well. Can anybody else to the details of those problems? A lot of it is stability. Does it work for months in your pocket? Kind of problems.
Right. One way, there are always going to be this, that, and the other formulations of batteries in the future, just like there have always been in the past. Going all the way back to lead acid, which is very, very old technology. Any kind of battery device, there is a energy capacity. There is a maximum input and output power. There is a specific energy, which is how much energy it can store in a given volume. I may have this backward. And then there's energy density, how much energy it can store in a given mass. And then there's how much it costs, either to build it at all or to build it at scale. So those are, no matter what, even if the technology is cheese and apple cores, it's going to come down to what's the specific energy, what's the energy density, what's the cost. Those are all the numbers going to boil down to, and whatever it winds up being, it's probably going to stink compared to liquid petroleum fuels, which are basically magic. That's why this is so hard to unravel, because gasoline, diesel fuel, kerosene works really, really well. So we're trying to. We have a very high bar to meet when it comes to doing any alternative to liquid fueled anything.
In terms of, in terms of speculative nanotechnology for like small scale energy production, there have been a lot of puff pieces, a lot of things recently making claims that, you know, maybe in the next 30 years we'll have piezoelectrics that are powered by radio waves or cosmic background radiation, for God's sake. Realistically, within the next 10 to 15 years, what do you think the efficiency curves are going to start looking like for metamaterials and other small-scale methods of, you know, power production for electronic devices like pacemakers and phones?
There's so much wrapped up in that. I mean, you're absolutely right. There are many puff pieces. If it says quantum or nano, it's probably fairly nonsense. If it says both, it's almost definitely nonsense.
Yeah.
Especially if you see it in a newspaper or on Facebook.
Yeah.
But that's not to say it's all nonsense. There's some really cool materials that they're coming out with that are piezoelectric, that like you squish them and release them and they generate some electricity. Those are very neat and have cool applications, like you said, for prosthetics like pacemakers that need tiny, tiny, tiny amounts of energy. And if we can get that just from, you know, going for a walk, like the same thing with self-winding watches, those kinds of like small amounts of energy, absolutely, next 10, 15 years, we can get some real cool stuff coming out of that. Your Fitbit being able to charge itself. Maybe.
Yeah, automatic wristwatches do it mechanically.
Yeah. So, yes-ish.
There are two things I know of. One is nanotechnology, nanotech fabrication processes give you a way to make small objects with insane amounts of surface area. And that can help you out when it comes to interfaces between materials in a battery. Something else I happen to know about, but I don't know what's become of it. There's with solar panels like we're used to, there is a hard limit on the efficiency they can hit for a single diode junction. I forget what that limit is. I want to say it's in the 30s, but don't quote me. Don't at me. And right now, state-of-the-art solar panels are topping out around 24-25%. It'll get a little higher, but unless you jump to something other than single junction panels, you're kind of stuck with that limit. There is something about using micro-machined arrays of dipoles, basically little antennas that are picking up EM radiation as though they're shortwave radio, as though they're crystal radio sets, just on a very, very tiny physical scale. I don't know what the efficiency limits of that. I every so often I'll read something about it, but I don't know where it's going or even if it's going.
Yeah, I mean, the nanotech idea is interesting. One of the biggest problems I've seen for things like hydrogen fuel is storage and transport. Like, would you like to carry around a gas bag full of hydrogen? Because that worked real well for the Hindenburg.
Compressed hydrogen. That's the thing.
Yeah.
Hindenburg was bad, and it was just a balloon.
Yeah.
You want to drive a car? That's compressed hydrogen. You want a highway full of those?
I might have shattered some lab equipment in a classroom once, accidentally using generating hydrogen through an exothermic reaction. Not all of the scarring on the ceiling in that lab is my fault. Some of it is, but not all of it.
I remember some stuff about maybe 30 years ago about using some sort of hydride material in tanks of hydrogen that kept it from shooting out real fast in the breach. But I don't know whatever came of that. Hydrogen has a thing where, because the atoms are so small, it can punch right through metals. My understanding is that systems that deal in high pressure hydrogen often has stainless steel pipes that are lined in gold. And over time, the hydrogen penetration will embrittle the metal. So it's often used in things that don't have to last very long. Now, when I hear people talking about hydrogen energy systems and moving large quantities of it around, I'm thinking, okay, you're going to move this stuff around at pressure? When are we going to get the gold-plated pipes in the discussion here? Or I don't. So I just hydrogen's just real hard to work with and dangerous.
Like, it's a great idea, but it's still a great idea. I remember when was it when I was in grad school or undergrad? I think it was when I was in grad school. So we'll put it at somewhere in the neighborhood of about 15-ish years ago, slightly longer maybe. Hydrogen, and the instructor stands up and says, hydrogen is just around the corner. And he walks a few feet, turns, just around the corner, just around the corner. Just comes back around to the same corner he was at. It's just around the corner. Just walking in a box. Never gets there. But it's gonna, just around the corner. Yeah, pretty much.
Let's go ahead and take the next question.
I was wondering if the achievement of ignition would reduce the 20-year mark for fusion.
Oh, we've had ignition several times. Ignition's not the challenge anymore. It's so getting fusion ignition to actually get a sustained fusion reaction, or not even a sustained fusion reaction. Ignition, we've got fusion happening. We had hydrogen, we turned it into helium. Bam! Awesome. That was the first step, took a long time. And we were convinced that as soon as we hit that, it was just around the corner.
Oh, yeah.
Then we needed a sustained reaction. So we need to sustain that for a while, and as soon as we can sustain that reaction, fusion's just around the corner. And then it turns out sustaining the reaction's not all that hard. It's hard. It's incredibly hard. But just sustaining it takes a lot of energy. We need the magnets that contain the plasma that's doing the fusing. We need cooling systems. We need things feeding in the hydrogen. And all of that takes electricity. And so now we need a net positive sustained reaction.
Right.
And that's basically what we're tripping on right now. And fairly recently, advances in magnets, advances in technology, advances in all sorts of things and materials, we've hit that. Somebody's like, yeah, we got net positive, which is incredible. But
For how
that
many nanoseconds?
means, that means fusion's just around the corner. It was nanoseconds, tiny fraction of time. We're like, yes, we've crossed that threshold, and now we've left the building and can start on our journey around the world.
As I understand it, fusion reactors of that sort start off with an array of extremely powerful lasers, all aimed at one point, a very tiny pellet of material. And those lasers, if I remember correctly, they're acting on that pellet through radiation pressure. Radiation pressure is not something we see in our everyday life because we don't live in a world where gigawatts of power are put in extremely small volumes. So it's just getting something that's sustainable the way a fission reactor is. It's just.
Yeah, the problem with fusion is getting it to start and keep going. The problem with fusion is getting it to start and keep going. The problem with fission is to get it to stop once you started it.
What are your feelings on a small-scale modular reactors for nuclear?
Small-scale modular reactors for nuclear power for fission?
Small modular reactors.
Yeah. I have feelings. Do you have feelings?
I not knowing a huge amount about them, what I can tell you is it falls back to that same thing of, do you want a large number of little things or a small number of big things? Do we have the social and industrial infrastructure to build and maintain a large number of devices like that and have them also operate safely? I agree. It would be nice if we had walk-away safe nuclear reactors regardless of their failure mode. Thanks to Fukushima Daiichi, now we know what happens if we take a reactor of that sort made by that manufacturer and just shut the cooling off. Now we know what happens. We need something that handles failure better. I don't know if that's the answer, But I hope it's something we can. I hope it's something we can get a handle on, because I don't think wind and solar alone and hydro is going to do it. We need something. We need firm power generation. That's what they call that. Power that you can dispatch as much as you want when you want it.
Yeah, I know a few people who work at nuclear plants, and it's an incredibly specialized skill set to maintain and operate those. So you need your specialists all in one place because there's not that many of them.
Not great, not terrible.
We seem to have made a lot of advances by doing what we want to do, but with less energy. Who's working on that?
Just lowering the energy demands of our everyday devices.
And increasing their efficiency.
Yeah.
You're never going to get, well, unless you change your technologies, like from incandescent to fluorescent to LED, you're going to have trouble getting more efficient lighting. We use the term an energy service. For instance, to put this much light on this much area in this table is a certain amount of an energy service that in this room is provided by, I guess, a mixture of LED and fluorescent lights. I can say I'll make do with less services. I'll have less watts of light power going through this square on the table, or I can change the technology by which I generate that light and get the same result for less power, for less electrical power.
And there are absolutely big gains to be made in places, but everything that we do that we use electricity for does, even if it's 100% efficient, that still takes energy. Like, if these light bulbs were 100% efficient, that means all of the electricity that went into them turned into visible light for us. That still has a threshold of watts to do that, and it's not that small. It's way better than incandescent, but it's not nothing. So it's definitely a place that people are working in a bunch of places. Electronics, lighting, heating. All heaters are 100% efficient unless they glow.
And even then, as long as that glow is not radiating to space,
yeah,
you get it back somewhere.
Yeah.
Maybe not necessarily where you want it, but yeah.
So I got a question about, like, while we have green energy, it's not green per se. Like, we have a lot of windmill graveyards. The biogas that she was talking about in Europe, burning stuff, and, that ends up being thermal energy, but we still end up with, methane runoff and everything. The biodiesel that we produce, that's still nitrous oxide, that's still smog. So, like, what are these things that are we doing to, mitigate some of these things that are coming off of our new green energy?
Well, here's one path. Electrify everything. You'll hear people kick around that phrase, electrify everything. But what that really means in practice is the things that you do now by burning a fuel, by oxidizing a fuel to generate heat, to turn into some usable form that you want, can that be replaced by a consumption of electrical power? There are so many. Transportation is like number one on the runway for addressing that. If you make that step to electrification, then suddenly you have a choice as to what your primary energy source was to generate that energy in the first place. If I drive a gasoline car, that gasoline's got to come out of a refinery that made it from crude oil. No, there are no other options, practically speaking. If I have an electric car, however, that electricity could have been made by nuclear, wind, solar, hydro, natural gas, coal. Then you have options. So if you go through that process of trying to have a post-fossil transition where you're drawing down the greenhouse gas generating primary sources, that's how you green ultimately.
Hey, green guy, you got any thoughts?
Yeah. So, I mean, the other thing to kind of note there is that when we're talking about, at least in my mind, when we're talking about making energy sources green, obviously climate change and global warming are the big draw there. But the other part, like you said earlier, coal has killed so many people.
Yeah.
And most of the green sources we have, most if not all of the green sources we have today, yes, there are costs to anything, whether it's space or an impact on the ecosystem. Coal has an impact on basically everything, as did oil, still does oil, actually. That I think any step towards moving away from coal especially, and I know they talk about clean coal, but without getting into a long and involved thing, it's not. It's still going to be significantly better to move towards these renewables from a greening and health perspective, honestly. It's not just about making things nicer for the ecosystems we're in. It's about reducing respiratory diseases or cancer incidents from coal and oil and any of these things.
I hate to end a really good discussion when it's going, but it is 9:30 and we are out of time. So thank you for great questions, and let's thank our panel for doing a great job.
Thank you so much for coming.
Thank you, everybody. Thank you. And
A couple quick announcements from me before you go. Please, if you liked this panel or have any feedback about it, provide us feedback in the DragonCon app. You will also notice a stack of neon-colored note cards at the other end of this table. We are doing a panel on Monday called Calculations We're Sad We're Doing, and we are requesting from you questions for calculations you would like to see our panelists perform. I am one of those panelists, so if you would like to see me suffer, do math, you can come back on Monday at 1 o'clock to watch that. But anything you've wondered, how long does it take a ferret to run around the Earth? What happens if you fill a nuclear reactor with Jell-O? I have no idea what you're wondering about. But whatever you're wondering, please grab a note card, write your question on it, and put it in that big gray box over there, and then come back on Monday. And reminder to put stuff in the bin for the DragonCon charity. And I think we are clearing this room that direction. So thank you very much and have a great night.
Thank you all.
Thank you, Jan.
And the next panel in here at 10 o'clock is This Year in Science After Dark Edition. So if you'd like to know about the science we couldn't tell you about during daylight hours, get back in line.